going to chair this meeting and also moderating the session with everyone. So today we have our speaker from University Science Malaysia, Associate Professor Dr. Asrul Nizam bin Abdul Manaf. He is a director at the Collaborative Microelectronic Design Excellence Center, or CEDEC, USM, and he is the leader of the CMOS-based Sensing Interface Integrated Circuitry and Power Management Unit IC, and also lab on printed circuit board and printable based devices technology group. And his background is basically he received his Bachelor of Engineering and Master in Engineering degrees in Electrical and Electronic Engineering from Toyohashi University of Technology, Japan in 2001 and 2005 respectively. And he completed his PhD in 2009 in engineering from Department of Applied Physics and Physico-Informatics, School of Fundamental Science and Technology at Keio University, Japan. And he has published more than 90 international technical journal and conference papers with 2 patents. And he also received IETEJ CBOS Memorial Award in 2017 and for the best engineering oriented paper. And he is also a senior member of IEEE and chair for IEEE Sensors and Nanotechnology Council Malaysia Joint Chapter. So with that brief background, so I would like to invite the next session to Dr. Asrul Nizam bin Abdul Manaf to share his expertise.
Okay. Assalamualaikum and a good evening. And then first I would like thanks to Prof. Nofitra for kindly introductions. And also thank you to TNC RNI, the TNC office UiTM, inviting me to share what is the possibility research collaborations, the potential collaborations between USM and UiTM. So let me share the screen first. Okay, everyone can see my screen? Okay, good. Okay, so I'm going to allow me to give some overview about my centers. So then I will give some overview about my current project, so that have a potential collaborations with UiTM, and some project I have already done one collaboration with UiTM. So the one project that we gone through with a MIMOS through the SRF funding. Okay, so that hopefully, so my expertise more related to the analog IC design, and then how we do the integrations with sensors together on the chip. So how that focus on the what we call the lab on the chip or the lab on a printed circuit board. Okay, so that my outline for this sharing session. So I will start quick overview about my center, CEDEC, and then that I will go into a few tema that I be considers we open futures potentials collaborations with UiTM team. So that finally I will summarize my talk. Okay, so my centers we funded by Ministry of Finance. We we got a top down from Ministry of Finance in 2005 and in the 2004. So that that established the centers in 2007, right? So actually these centers are mainly to focus how can bridging the gap between the academia and also the industries that relate on the IC design and also the sensors technologies. So we are started in operation in 2007, and then after 6 years, so this center was appointed as a COE, the one of the Center of Excellence under Senate USM. So then last year on March, we was appointed as one of the COE providers under NCIA, the North Corridor Industrial Authorities, specific on the circuit design and the IC design. So in terms of our main powers, we had 18 staff, and out of 18, we have the 5 staff academic, 7 permanent research officers, and the 4 technical staff, and the 2 admin staff. And in terms of the postgrad, we have a 35 postgrad. So that supervised by the 5 staff academics and 14 PhD and 21 master's students. So for linkages, we had a collaboration with a few local fabless design house, such as like Opstar, Skychips, and some collaboration with the multinational companies, the ST Micro and Global Foundries. And recently, we had an agreement with TSMCs for a chip tape-out services. So for international linkages between the academia, we work with Toyosu University of Technology from Japan, Tokyo Universities, and with China, 2019, with Xiamen University of Technologies, we collaborate on establishments, the Industrial Internet of Things, how the collaboration between USM through a CDAC, Xiamen University of Technology, Opstar, and Kevin Core, that we develop the centers Internet of Things at Xiamen, and we have worked with the NCTU, Tuan, Australia. So the role of CDAC, so what mandate by the national, by the government, and also by the Minister of Higher Education. So actually, the one we talk about the semiconductors industries. So that cover from a front end to the back end. So the main role of a CDAC, so to how to accelerate the activities or how to assist the teaching and learning in IC design. So the one of the common that what we got a feedback from industries, how to make the student familiarize with the modern EDA tools in the chip design, because chip design now they have designed more billion transistors, right? So that means we need like the automated tools. So with that initiative, that motivation, so in a CDAC, we park all the EDA tools, mentor, graphics, cadence, synopsis, and then we get all the university can access to us. Mean when they access to us, and then they will do the design the chip, and then they will send the file to my team, and then my team will do a checking and make sure the file is correct and clean, so that we send to the foundry for the chip tape out. That means the chip to the chip fabrication, and then they will receive the die, so that we give back to the lecturers or the researchers. That means to complete their die, either to do the package and to the proceed on measurement. So that what we have the 31 university that consortium. So UiTM, the one of the members in that consortium, so that can be able to access lah. I mean to our facilities, our EDA tools, so they use for the teaching and also for the research. So back to our focus research areas. So in a CDAC, so like I mentioned, we was mandated to focus on the IC design, so and also the sensors. So what we did, so we have a group how we focus on the analog design and the digital design. So when we have the circuit, so that we be able to integrate with the sensors. So how we develop by group sensors. So I mean we have the chip, and then we can do the integrations on the silicon or either on PCB, how we call the lab on printed circuit board. So it means so any the signal from the sensors, so that can be amplified by the circuit, convert to the voltage, so that can be for the later processing. And recently, the from the last years, what we have the demand from the Penang semiconductors industries about the research in advanced packaging, like the signal integrity, the interconnect, and then we started a small group that how to focus on the fundamental in advanced packaging, such as like 3D packaging, 2.5D packaging, and also how to design a very fine circuit trace or the very fine interconnect that with that by do the modeling and simulation in terms of the signal integrity, the loss, so that we create the one group specific focus on the packaging area to support the demand in advanced packaging and also the chiplet technologies. So when we when we do the design, actually we need the foundry, I mean to do the tap out, I mean to fabricate the chip, right? So we have a collaboration with the Silterra, so mean to provide the technologies to all the researchers in IC design, so to design the chip using 130 nanometers and 180 nanometers chip and the process PDK, then to design the chip. But for us, for our internal research, actually we also are tied with other foundry, ST Micro, and global foundry, and recently through what TSMC, through the ADFP program, the Academia Development Foster Package program, we recently did the agreement between the TSMC and the TSRI, the Taiwan Semiconductor Research Institute, so that can be the enable our researchers to access 16 nanometer the FinFET transistors, mean to do the digital IC and also the analog chip design. So as a CDAC, we want to be known as the fabless integrated academic research centers. We do the chip design, but we not mainly focus mainly on the foundry or the on fabrication. So that what the example chip that we already done by our researchers in CDAC, so that we have a 5G chip, how that the 5Gs and the transceiver chip, how developed by the group under the transceiver group. So this group was lead by Dr. Jaga Deswaran. So how they are more focused on the transceiver component, the power amplifiers, the transceiver chip, so that towards to the 5G and the 6G application. And then we also have a group that focus on the DAC and the ADC. So that's the one of the LED drivers that how they fabricated through the SFAB, through the with for the as a LED drivers. So that how the collaborations between OSFAM. So that one of the example, the digital IC chip by the group digital. So there's some research related the the cryptographies and the digital transceivers. So that what I mentioned just now. The one of the group that are focused on the advanced packaging and then the signal integrity, the interconnect loss. So that how to support the demand and to understanding how to increase the performance for the 3D ICs, the 3D packaging or the 2.5D packaging, for example, any the application in the chiplet. So in term of the sensors part, so that how we so when we have the chip, we design the chip, and then so when we receive the die, so we do the packaging, and then that how we apply in any the sensor application. So how we call the lab on printed circuit board or the lab on the chip. So in the sensors group, we are focused on the sensing principle related to electrochemical sensing or the MEMS register based sensing and the FET based sensing. So we develop the sensors, we do the sensors fabrication. So because the sensors we miniaturize, we make the sensors become a smaller and smaller. So that's why the output signal will become lower. So that's why we need the chip design, the ICs, so how we can integrate the hybrid integrations with the sensors to amplify signal and convert it to the voltages. So that what we call the label-free sensor. So they one of the sensor that we developed in my lab, in my centers. So we did some proof of concept how we can do the integration between the microcontrollers and also the fuse circuit in that the TPU, Teflon polyurethane. So this is not only can bendable but can stretchable. Right. So they one of my research officers, they try to print it the sensors on the PVA, what we call the polyvinyl alcohol. So this substrate, so that means the one you heat up, so that can be eliminate. So this pattern we we be transferred to on your skin, right? So this one of the example like we did from our previous grant. So that how we did the collaborations between my centers and Inform. Inform is one of the high COE for the Institute Molecular Medicine. So that how we as an electrical electronic engineers, so we develop the transducers. So that what our transducer is the electrochemical transducers, and then we do the miniaturization. So then when we miniaturize, so we do the integration with the microfluidic that we integrate with the microcontrollers. So that what we call the lab on chip, the lab on a printed circuit board. That's one of the project that one of my senior research officers, how they done the and kacung to one for the power measurement unit ICs for the artificial retina. That means to power up the photodiode, right? So that what the few research that what we done in my group. That means from the chip design. So when we have the chip, so we integrate the chip with the sensors, so that towards to, for example, for IoT edge devices or for yes for wearable and the flexible electronic application. So for today, because the title given to me, the uh, exploration research opportunities between the USM and UiTM. So that I will explain what type of the research that done that is more detailed so that we can open any potential collaboration, and I will open any discussion to all the participants today. So like I mentioned, the one of the project that we done, how we do the development, the sensors on the PCB. That means what we call the lab on a hybrid printed circuit board. So what is this? So the one we talk about the biosensors, right? So the current equipment in the hospital, right? So they bulky, right? Mean we need the expertise to operate. That mean to do the processing, right? So when the system is bigger, mean they need more a sample for the detection. So the one of the ideas that how we call as MEMS, the microelectronic mechanical system, but the MEMS is more focused on the silicon. So what our group focus, how we be able to transfer all the functioning on the lab, for example, the functions of the weight scale, the functions of the pipette, how to be able to act on PCB. So what we call the lab on printed circuit board. So that means the on PCB, so we can create the micro channel. So that means so we can inlet the blood or any the sample, so that they we go through in the micro channel, and then they will come to the sensing part and then do the detection, and then the signal we amplify and convert to the voltage. Right. So that what we did, what we call the lab on printed circuit board. So mean in the printed circuit board, they have can how we can translate the whole lab, the whole system, the chemical lab or the diagnosis lab on a chip. That mean on a subset. That mean on right now in our case we translate on the printed circuit board. Right. So what we did, so that what we have the conventional electrochemical. When we talk about the electro chemistries, mean we have the three working electrodes, the counter electrode, working electrodes, and the reference electrode. So that what the conventional system, we need the the three electrodes, and then we need to put in the petri dish. So, but this size is big, mean we need a lot of the solution if we want to test using that system. So how we can translate this conventional electrochemical setup to be as a chip, right? That means on a chip. So that's how we design our own the electrode of electrochemical sensors, and then we fabricate the electrode on a PCB that easier to us to to integrate with the microcontrollers. So that what we did. So one of project that we done we in 2020, and then just conclude just complete this project this year's we got under Crest Grant, how we work with the Inform Institute of the Molecular Medicine. So how my centers we focus on the development of the transducers. So we design our own sensor. That's why if you are familiar with the electrochemical, you have familiar with the drop sense, with a pump sense, and then that we how the electrode is different with us. So we have a proper calculation. That means the proper analysis to come out the optimized electrode. So that one of the project that we done. So this electrode we work with Inform for a typhoid detection. That means to detect the salmonella. So we use the gold electrode. On top of the gold electrode, we modify with the graphene oxide. So that we can attach with the amine, the amine, and attach with the link the aptamers. So that we do for the for the salmonella. That means for a typhoid detection. So the one we have the sensors, and then we do the integrations with the microfluidic, so that we do the integrate with a microcontroller, the chip, so that can be able to detect the reading and wirelessly transfer the reading to computer and to the dashboard. So the one of this, and then we using the same concept of the salmonella, the same concept, the same sensing principle. So actually we try to test it uh with a SARS-CoV detection. So it means the same electrode, but we change the bioreceptors. So from the typhoid bioreceptors, we change to uh the 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 DNA, but for the specific for the SARS-CoV. So one of the published papers that we already published on the lab on the chip journal. So that under Royal Society Chemistry. So, but for today discussion, Chelis, uh, for this electrode, we design the two type of the bioreceptors. So we design with the for the aptamers as a bioreceptors. The one of the second type we attach with the DNA as a bioreceptors. So we have the one type, the aptamer based sensors, and the DNA based sensors. So but the problem with our current the aptamer based sensors, because we rely on the graphene oxide modification. So the one we do the testing with in terms of the sensitivities, right? So it's a very low, it's less than 65%. So I mean, so the one we get, the one we tested with 30 samples. So how the 30 sample, they have a patient, the food handler, the how we have the salmonella. Let me have a typhoid, but the result we get only less than 65%. But the one we test with the healthy patient get good about 96.6%. So that means the one of the the need some some modification, and then research how to make it a stable the graphene oxide, the one we do the attachment on the gold or any the others uh, amine, the COH material, so that can replace, so that can be improve our sensitivity. But the one type of the how we use the DNA sensor, how we use the pure gold, so we give a good result even though for the sensitivity and the specificity. So the same electrode we apply to the SARS-CoV, and then we be able to detect even though one mismatch gene, that be able to do the they be able to differentiate the signal. So this data we done published on the last years in the lab on the chip genome. So with that outcome from this type, actually we further collaboration with the Inform and the one companies. So how we want to extend it the one electrode type. Right now we just develop the single electrode, mean they only can detect one disease at the one time. So what the next, we secure the one grant under the CREST. So how we to integrate more, not only the one electrode, but to make as a array of the electrode. So by having the array of the electrode, so that can be detect so the one we give the blood the patient a sample, so that be able to detect simultaneously. Because what I discussed with our partners, So like the tripod, they have a 5 type of the tripod, right? So that one our next project lah. So that one of the potentials collaboration, because we have the element of the electrode modification for a 5 types of the salmonella. So the one from that output, that means how they need to connect with the multiplexers, the SOC circuit, that means to do the amplification and convert them to be the digital to the digital signal. So that one of the project, how we have to integrate, we do the extension from the single electrode to 5 electrodes and integrate with the digital microfluidic to control the movement of the sample without pumping, and then they integrate with the multiplexers circuit and then with on-chip potential start, right? So and then the second team, so what we can do together. So because that is the correlate with this program. So because we have the 1 sensors, 2 sensors, 3 sensors, 4 sensors, so the each sensor is the electrochemical sensors. So how we can translate the signal from the sensors and then up to the on chip CMOS, I mean the on chip, the SOC. So the second group in our team, so how we can have the sensors, but how we can integrate the 5 electrode with the potential start sensors, and then with the sample holding. So mean that can be, so all the potential start can be as a on silicon, so that can be easiest to do the integrations with our sensors. So mean the one they have the signal, so that mean the first electrode they do the sample holding, sample hold, and then that we do the scanner, and then that convert to the digital, and that can be appear to the dashboard. That's why. So this we need some so we have a lot of the block components here. So first we need the FPGA, I mean to control the timing, and also and then the FPGA also to need to control the DACs to the chip, so the potential start chip. So that we open any the collaboration, so how can related to the IC design and any the FPGA design. So the others in IC design, so the one we have the sensors, and then we have the potential start chip, but we also need the PMU ICs. So this a project also one of the project done by one of my PhD student, right? So that did the block of the PMU IC. So that for the for the low powers. That means for a low powers the IoT device for the wearable electronics. So the one, then the another project that what we have with a partner from the Fabless Design House, how we want to develop the ASIC, the AI chipset, but using the ASIC. So that we using the RISC-V. So that what we have the RISC-V, and then that we have all the analog block. So that how we can do, because the one to complete the one chipset, we need a lot of the IPs, right? So mean cannot be only done by solid as a USM or the CDEC. So that we have any the furthest collaborations, right? So it means from any the group digitals, so any from the firmware group, so that be a complete the workable ASIC chipset. So that one I give some ideas how in our group. So mean we have a development of the SoC for the potential start, and also for the ASIC for AI chipset. So the one of the other tema by one of our group in a CDEC. So we also how to develop so like we did for lab on printed circuit board. So like I just explained just now, we use the rigid PCB, mean we use the FR4. They cannot bendable and then cannot flexible. So one of the tema in our group, so how we can extend not only the rigid PCB, how the possibility to develop the sensors on the flexible or on the stretchable uh, subset. So what one of the idea we work with Swim, how to have a smart bandage. Mean when we have the bandage, but the current bandage that only just a bandage. Mean so they cannot give to us what the real condition of our wound. Right. So what we are going to start the collaboration with, that is still in the preliminary studies. So the one of the papers, so how to identify the level wound. That wound is a critical, the level 1 ke level 2 or the level 3. So the parameter is depend on the pH, right? So so the pH and also the oxygen levels. So mean um so by knowing, so if our pH is more alkalic, so mean that can easiest to grow the bacteria. So the one of our project with Shirim, we still in the preliminary studies how to, that mean the how to attach the bandage that developed by Shirim with the pH sensors. That means just to identify the pH value. So from the pH value, how we able to correlate the amount of the bacteria, so that we can correlate at least the level of a wound. That means, is it your wound is a critical? So I mean, the one you come to the hospital, so the based on that data, so doctor, okay, you have to replace the bandage, or you still no need to replace the bandage. Right. So mean to 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 attach the pH sensors on that bandage, we study so what is a smallest thickness. So that can either the one you attach, so the sensor we able to stick on that bandage. So that one of the paper done by the De Hyung Kim. So to ensure your sensors can follow the the what we call the curve structures. So at least the thickness of the bandage less than must be 5 micrometer and below. So that what we do the collaboration with the polymers researchers, how can develop to us a very the ultra thin film, and then that we can try to print it on the our pH sensors on the film. So that what the still in the preliminary. So actually our partner, they done a few recipe. That means to develop a very ultra thin film. So that our lab, we design the simple electrochemical sensors, and then we try to print it, and then see the, is it possible can able to do the pH. I mean for the pH measurement. But we still on in terms of the recipe, because the one we do the heat, we see the material start to, that they compress and then stress. So at still in need to more optimization in term of type of the film, and then in term of the printings technique, and then the cure technique. So and then the other project that what we done with UiTM, so that the partners with Prof. Rasidi from the UiTM Penang, so that with a PhD student also the UiTM Penang. So that how we through in with a CDEC, and then with a memos through the SRF. we done develop the flexible antenna with the food sensors. So actually the the idea of this project, actually we want to have food sensors, that means to detect the, for example, to detect the freshness of the meat. So that means this sensor we can attach on the packaging, and then we need the antenna as well. So the one you are consumer, you come to that supermarket and then you just use your handphone, attach to the packaging, and then they will give you the meat already 7 days in the supermarket. So that you know, and then they will give you the freshness of the quality of the food. So for that we focus first on the antenna part. So I mean how to have the flexible antenna that be easier to attach on the food packaging, all on the like a meat, right? So meat, so how they wrap to get to on the meat, and then how we can attach the flexible the antenna. So through collaboration with Mimos, and then the antenna designed by the UiTM PhD student. So that we did the collaboration with CDEC. How we CDEC we focus on the circuit design. So they one of the example of the antenna design, and then with a circuit design, we use the Texas instrument. So that how we develop on the same flexible, I mean on the flexible substrate. So this one, the one of example demo to show that what the antenna is working. So you can see, so the one they attach the handphone on top of the antenna, so the temperature sensor give the reading. So when we get the sensors, and then we touch to the hot side, and then we can see how the signal is increasing. I mean they detect the hot temperatures. So but the good, if this by using that antenna, we no need the batteries. So we using the near field communication to harvest the energy, and then to power up the sensors. So that one of the examples and then so when we transfer our sensors on that on the front side, so we can see how the reading of sensors will become lowest. So from that prototype, we see so our antenna is working, can harvest the energies, and then can turn on the sensor and microcontrollers. So that what we have a fully flexible, not only, so this first prototype, the circuit we fabricated on the polyimide is not the stretchable, it's not the flexible. But here we put a concept how the antenna and also the circuit all on the flexible subset. I mean on the TPU lah, right? So that what we some of the samples collaborations between UiTM and my team. So and then the others, we also do the still in the flexibles, we do the strain sensors. That one of the example we do a testing on the bender, and we see, and then we print it with a carbon, so we can see how it is sufficient to power up, I mean to conduct the electrics. So I mean this can be a flexible to further improvement to develop any sensors application. And then so when we did the flexible work, so we see how the design of the PCB will be a different. So how we need, so the normal PCBs, you no need consider about the edge side, but when you design on the piece, on the flexible, the stretchable, so you have to change the design rules. Mean we need a curving, that we need a curve to avoid the stress. So to avoid the stress, the when you stress, or you stress the when you stress the substrate. So that's some of examples. So we did also some on PVA, band-aids, also was some on the gelatin, right? So just to see how the possibilities lah. So any the various type of the substrate. So in terms of lab on printed circuit board, the lab on a chip, we still have a lot MT can do because we don't have any standard yet. Now the PCB only have the circuit design standard, but they don't have any standard yet with to do the integration with the sensors. I mean, not any design rules for the lab on printed circuit board. So that's why the one of our idea team how we can work with the industries to provide, that mean to develop the design rules. I mean from the circuit up to the sensors integration. So as summaries, I introduced to you what our current research, so that how we can open to any the collaboration in terms of the chip design or any sharing facilities and any for related to the sensors design. Right. So, but in terms of the electrical electronic, I have recently have a meeting under National Semiconductors the Strategic Force with a meeting. So EE for the national agenda that we are focused on the wide band gap materials, and then the the IC design, the wide band gaps materials, ATE, the automated testing equipment, ATE, and also the advanced packaging lah. So if you have any ideas or any the innovation related to wide band gap, IC design, the automated testing equipment, the ATE for the IC testing, and the advanced packaging, a lot of the potential grant through the SRF and then through MOSTIS. So with that, there are the announcement from my team, my partner from Schools of Materials, School of the biologists, and also the partner from outside from UiTM, MIMOS, and also from the Inform. So that my team lah, that means for the sensors, and team from sensors from the School of Chemistries. So how we work together to end the innovations for chip and biosensor. How we do some when the microelectronic engineers meet the biologists, meet the chemistries, so a good more innovation can do that can be the impact to the society, to impact to the communities. So with that, thank you. So I open any question. Yep. Thank you.
Thank you, Associate Professor Asrul Nizam. I think it is a very wonderful and very fantastic research conducted by SEDEC teams and the members. So I would like to invite all participants for asking any question related to the topic or projects that has been shared by Dr. Asrul Nizam. Okay, I think maybe I can ask first one question to Dr. Asrul.
Yeah.
I think there are so many polymers, I mean in terms like biopolymers, but I saw that in your work that you are using chitosan materials.
Yeah.
Yeah. Any reason or why you choose that specific materials?
Okay. Why I use chitosan, because the what we have the problem. So because we have the gold electrode, because we design the gold electrode, but we need the any nano materials, I mean to improve the surface that can improve the current, so that we improve the limit of the detection. So based on our experience, so the one we direct attach a GO on the go electrode. So the one we attested, so mean the GO remove, they pay off, remove. So that affect our sensors credibilities and the repeatabilities. So that's why we apply the chitosan, the one of be like the adhesive to ensure the reliability of the GO. So the one we attach on the gold, so that can be like just function as a adhesive layers lah to our electrode, to our electrochemicals electrode.
Okay, thank you, Dr. I think we have one question here from Dr. Muzamil. The question is, have you had any experiences utilizing conductive polymers in some part of the sensing materials?
Okay, the one of, okay, can I say the slide? Okay, so I think anyone can see that slide, right? So actually, the one we started design the stressable mean the substrate mean we are target for a stress sensor application. That mean for the stress sensors application. So so the mean the one we stress, right? So the one we when the substrate is stretched, so the stress sensor also must be followed to stress lah. So that must have conduct the current. So we so we have a few so if we use a normal metal, right? So like a normal metal, but the one you stress, so the metal they don't have the like the polymer behavior. That means how be able to stressable, and then that can be a payoff. So to overcome the problem, what we did, we use here's one type of the polymer. We use the PDMS, the polydimethylsiloxane. But the polydimethylsiloxane is pure polymers lah, but it's not conductive. So what we did with the one of my partners lah, that means from the chemistry, because I'm not the chemist, but I'm the electrical electronics. So that means how they did, so they do the optimizations of the recipe of percentage of the civil particles in mean on with the PDMS. So they mix the percentage of stable nanoparticles with the PDMS. So that translate the PDMS to be the conductive polymers lah. So now the ink that I show to you, that is the PDMS plus visible nanoparticles. So that is a polymer conductive. But the polydimethylsiloxane, we mix with the silver nanoparticles. So that we tested on the TPU. So that's why the one we stress, so that is not that the circle, the sensor also can be follow the stress and they not pay off. So and then you can see that we have a lot of the electric components here. So that this concept we want to prove the flexible hybrid printed circuit board. So the green color is a normal printed circuit board that rigid. You cannot do the bend, you cannot bendable, cannot flexible. So here's we want to prove one our project to prove how to develop flexible hybrid printed circuit board. Mean in the PCB is a flexible and stretchable, but the component is rigid. Right. So the one of our issue, so the one I do the solder, the one I assemble the widgets on that flexible. So normal we use the conductive paste. The conductive paste is metal. So the one we stress, so the paste also we open and then the component we peel off. So with that we also use the polymer conductive paste lah. The polymer conductive paste, I mean to so one you stress, so the paste also will be stressed for follow the stretching, so that component can remain on the PCB. So but the one of problem, the one we meet with this the PDMS with a silver nano particles. So the one we do the printing technique, we have a lot of issue in term of the the clot, so the nozzle is clogged with the particles. And then we also have some issue to control the viscosities, so that and then the effect to our cure lah. So but for this part is not we pass to my partner lah, that mean our polymer expertise. So that means from our side we just provide the what we need in term of the electrical spec, and then in term of the sensing specification. So we let the group chemistry and polymer do for us lah. I mean do the formulation. Yeah.
Okay, thank you, Dr. Asrar. I think it's a very interesting topic this evening. I hope that everyone has a very fruitful and insight informations from Dr. Asrar. Before we end the first session, we would like to take some photos. So I hope that participant can switch on your camera so that we can have a photo session together with Dr. Asrar. Sure. All right. All right, so ready everyone? The secretary will take photo. Just maintain your smile on the face, on the video. All right, 1, 2, 3. Okay. All right. QR code. Oh, QR. Okay. We will share a QR code for the attendance record, as well as we also will share a link to the next session. So we would like to invite participants who are interested to initiate the collaboration with SEDAC to join the closed session after this meeting. So please refer to the chat box, and also we will use that link for the closed discussion with Dr. Asrar.
So I saw the one question from Hadi. I think Dr. Hadi.
Yeah, I think I just saw one question.
Yeah.
Yeah, one more question.
Yeah, about the capability of the integration, right?
Mhm.
So actually, the question, what are key opportunities in the integrating the sensors with silicon-based CMOS lah? Okay. So the one we talk about the heterogeneous integrations. So some sensors we cannot do. The one we talk about the chip design. The chip design they talk about now the 5 nanometers. Intel talk about 18A 1.8 nanometers. So this not applicable good for memories or for the logic circuit. But in terms of the sensors, so we can remain so the all technologies, that mean 180s, the 130 nanometers, but by using the heterogeneous integrations, so I mean in the one substrate, so we be able to the integrates with photonics, and then we can integrate with the other type of the sensors on a same platform. So that can be improve the performance or can improve the functioning of the sensors, but we can apply, I mean the using the lower process node lah. So it mean the good for the heterogeneous integration that can be diversified the functionings of sensors with a same platform lah, the same substrate, I mean the same platform.
Sila ikuti perkembangan dan info-info tentang penyelidikan dan inovasi UiTM di kesemua platform media sosial kami, terutama di Facebook, Office of Deputy Vice-Chancellor Research and Innovation UiTM dan juga Instagram kami
answer all the question.
UiTM. Dan jangan lupa untuk menekan butang subscribe di YouTube.